See a picture of a diffraction grating up on the board again with two openings. When a wave, whether it's a water wave or a light wave or a sound wave or any other wave, comes and encounters this barrier, we're going to find that part of the wave goes through the two openings. In both cases, we get diffraction taking place. Diffraction was the spreading out of a wave. So the wave, again, sound, light, water, whatever, is going to spread out around these two openings. Now, if it's a water wave or some other wave that's visible that we can see, we're going to see areas of constructive and destructive interference. They're going to manifest themselves as lines. We'll get a line of constructive interference taking place right here. Then we'll get a line of destructive interference. Then we'll get a line of constructive interference and destructive and constructive and destructive and so on. We get a whole bunch of different lines of constructive and destructive interference taking place. Now, if this is a light wave or a sound wave for that matter that we can't see because it needs to be reflecting off of something in order to see it, then the only way we're going to see this, the only way we're going to actually be able to observe this interference pattern is to put a screen down here. On this screen, you will see a bright spot. The bright spot corresponds to the first line of constructive interference. We also call it an antinodal line. A bright spot, a maximum, an antinodal line. It's where we have constructive interference. Crest meets crest, trough meets trough, bigger crest, bigger trough, constructive interference. Right next to that, we get the area of destructive interference where crest meets a trough. That's the dark spot on the screen because there is no light. The crest has canceled out the trough and the light has disappeared. Right beside that is another area of constructive interference. Destructive, constructive, destructive, constructive, and so on. We get the same thing on both sides. These bright spots that you see on this screen, again, we call bright spots, we call antinodes, we call maxima. The dark spots in between those bright spots, we're going to call dark spots, minima, nodes. Okay, let's number these. The first bright spot, 0. 1, 2, 3, and so on. 1, 2, 3, and so on. The minima in between would be 0.5, 1.5, 2.5, 3.5, and so on. Now, we introduced two equations last week that describe the pattern that you see up above here. First one, lambda is equal to d sine theta over n, and then lambda is equal to xd over n times L. Lambda is the EZ variable. Okay, that's the wavelength. The wavelength of the light, and it's almost always going to be in that range of 10 to the minus 7 meters. If you're solving for it and you don't get 10 to the minus 7 meters, you've made a mistake. You've probably forgotten to convert centimeters to meters. It's probably what you've done. What else do we got here? Tell me, please, what this distance is right here from opening to opening. What variable is that? Is that d? Is that theta? Is that n? Is that x? Is that L? It's d. It's a little d. Yeah. Good. Easy enough, right? Distance between the slits, going to be a little d. What about this one right here? This distance right here. It's L. Good. The thing that's kind of confusing about this, as far as I'm concerned, is that we've got so many things that are distances, that are meters or centimeters, right? Lambda is in meters. D is in meters. L is in meters. This is in meters, whatever. Whoops. I was going to say whatever that is. X gave away the answer here. X is in meters. X, by the way, is defined as what? The distance between maximum 1 and maximum 3? Could be. What else could we define X as? I could go around the room right now like we do in elementary school and say, have everybody give me an answer here, and everybody could give me an entirely different answer and still be correct. Generally, what does X mean? Callum? The distance between a maximum? Did you say, or the difference? Let's say the distance. X is going to be the distance between any maximum or minimum and any other maximum or minimum. So it could be from max 1 to max 3, as we have drawn there, or it could be from max 1 on one side to min 3 on the other side. It doesn't matter. It doesn't matter as long as something is consistent with that. What variable has to be consistent with X in order to make this work? Which one? N, yeah, N. What's N going to be in this case? Going from max 1 to max 3, N's going to be, Victoria? 2. What's N going to be in this case? We're going from max 1 to max, well, it's a minimum, to minimum 3. Minimum 3 is kind of like saying maximum 2 and 2.5. So 2.5 minus negative a half. Sorry, 2.5 minus negative 1 would give me, N is 3.5, right? Make sense? All right, so we've got D, we've got N, we've got X, we've got D, we've got L. The only thing we don't have here now is theta. Theta is what? An angle, but what angle? Yeah, right? Let's not say critical, because that's relating to refraction and total internal reflection. This is diffraction. I think you're on the right track. It's the angle as measured from the central maximum, always from the central, to the second order maximum, or to the third order minimum. It doesn't matter. From the central maximum to some other maximum or minimum, okay, theta, measured in degrees. Well, and it can be measured wherever we want, as long as it's from the central maximum, as long as N is consistent with it. What would N be in this case? Yeah. What would N be here from 0 to 2? 2. What would N be in this case when we're going from 0 to the third order minimum? And it would be 2.5. So now we're good with theta. And again, as long as we're consistent with theta and N, then we should be good to go. Yep. What's interesting, N and X? X is a distance, physically measured in meters. So let's say the distance between Donovan and Tyus right now is 3 meters. Okay? Literally in meters, X. The number of people between these two guys, 1, 2, 3 people. N is a number. X is a distance. Does that make sense? Okay. X is the distance between one maximum and another. N is the number of maxima or minima that's encompassed by that. All right, you had 6 questions. The first 3 were on page 689. Any issues with those questions on page 689, please? Yep. Number 3, was it an issue with the color? Or, okay. You won't have to find a color. You'll have to identify what type of EMR it is, perhaps, whether it's visible light or ultraviolet or something like that. And we learned how to do that at the beginning of this unit, right? But as far as the specific color goes, you won't have to do that. Okay.
And also when it says like the slit, that means N is 2.
No. Let's do number 3. Let's do the whole thing, okay? Okay, we've got the second nodal line. I want to draw attention to that because a nodal line is a minimum, right? Antinode is a maximum. Nodal line is a minimum. Let's draw this. I always like to draw this for all of these questions. The second nodal line relative to the central antinode. Here's my central antinode, 0. Here's my first bright spot. Here's my second bright spot. Here's my third bright spot. The second nodal line is right here. What would N be equal to there? The second nodal line, this is the first nodal line, right? This is the second nodal line. The second nodal line occurs between 1 and 2, therefore we'd say it's what, Jesse? 1.5. 1.5 minus 0 is 1.5. So N would be 1.5 there. Jillian, does that make sense?
Yeah.
Draw it out, guys. Seriously, like especially when you're dealing with a nodal line, right? A minimum, because you're dealing with the halves. I find it really helpful to draw it out. Even the antinodes, though, becomes helpful to do that, I think. Yep.
It's weird that it's antinode.
Yeah. No, I agree. Instinct kind of tells me the same thing, right? That the node should be the bright spot, but it isn't. Okay, so N is 1.5. We've got an angle here of 0.095 degrees. Another thing that, for whatever reason, I'm not sure why, but instinctually, is that a word? We're going to say it is. Okay, instinctually, we're going to say that's a word. That 0.095 degrees, as soon as I see angles that are really, really small like that, for whatever reason, radians come to my mind. I start thinking about radians. Okay? We never deal with radians in physics 30. Okay, I don't care what the angle is. I don't care what number you see. You're always going to go degrees in physics 30. Okay, never radians. So remember, I know you come from math class and you're in radian mode. Okay, flip it to degree mode here, because that's what you're always going to do in physics 30. 0.095 relative to the central antinode. The two slits are this far apart. That's going to be D. We're going to make sure that we circle that millimeters because we don't want that. What's the wavelength? The color we won't worry so much about. Lambda, we got two equations here. We got d sine theta over n, and we've got xd over n times L. Which one makes sense, I think, in this question? Yep. Yeah, d sine theta over n. Okay, and this equation is always valid, right? So we don't have to ever worry about, it's not valid in this situation. It's always valid as long as it's a double slit experiment. D is 0.40 times 10 to the minus 3 meters times sine of 0.095 degrees divided by n 1.5. We do that math, it works out to be 4.4 times 10 to the minus 7 meters. We should expect to get 10 to the minus 7 meters. That's visible light. How would we know it's violet? You don't really have to be able to do that. But if we say F is equal to V over lambda, I think when we do that math, I think we get something like 6.8 times 10 to the 14. Somebody want to try that quickly to make sure that I remember that right? What was the range of visible light? 4 to 7.5 times 10 to the 14? Was it 4.5 to 7? I think it was 4 to 7.5, wasn't it? Yeah, I think it was 4 to 7.5. Yeah. Double check that in your notes, guys, from earlier on, but I think it was 4 to 7.5. Is this going to be closer to red or violet? Okay, so 4 to 7.5. This is going to be closer to violet, right? Now, honestly, if I saw that number, would I know that that's violet? Probably not. I would say that it's, okay, looking at it myself, I would say, look, it's either going to be indigo or violet, because clearly it's a lot closer to violet than it is to red. Right? It's close to the 7.5 times 10 to the 14, but I wouldn't know exactly what it was just by looking at that. Okay, we know it's visible light. And if you've got an option if it's violet or red, well, you know it's violet, right? You got an option that's violet or indigo? I'd have to guess on that one myself. So you're not going to have to be able to do that, unless your options are like violet and red. Okay. We also had 3 more questions on page 691. Now, I think you would have found when you did these questions that the equation that you would want to use for each of these is lambda is equal to xd over n times L. But there might be a problem with that equation for some of these questions. What is it? What's the issue with this equation that we may or may not have run into yet? Connor? Yeah, it doesn't work for big angles. So if we go back to the diagram, this diagram, if theta is more than about 10 degrees, then that equation is not a good approximation. Even for small angles, it's an approximation. But it's a good approximation, meaning that, look, gravity is not really 9.81 on the surface of the Earth. It varies, but it's a good approximation for us. So we use that, we get numbers that work, right? That equation, that's not really correct, xd over n times L, but it's a good approximation as long as the angle is small. The angle is big, bigger than 10 degrees, it doesn't work for us anymore. So what we technically need to do before we use this equation every time is check and see what the angle is. But to me, that's a little bit too much work. As far as I'm concerned, look, if we're going to find the angle, and we're going to find that it's 12 degrees, 8 degrees, 2 degrees, whatever, if we're going to find the angle every single time we go to use this equation, then why don't we just go back to use this equation every time and find the angle? It defeats the purpose of even having this one, right? If we've got to find the angle to check to see if it's valid. So my suggestion is do a quick little check. Do an approximate check. Let's compare L to X. If L is greater than 10 times X, we're good to go. If it's not, then we're not good to go. So literally take the value of X, multiply it by 10. Is L bigger than that? All right, go ahead and use it. If L is not bigger than that, then let's go back to the other equation. Find the angle and use it. Yep. Yep. All right, any issues with these three questions, 1, 2, and 3 on 691? Good? Is your hand going up there? No? No problems? I think if I remember, all of these problems had L bigger than 10 times X, is that right? So we were able to use this equation. What if it wasn't? What if we looked at question number 2? We've got X, we've got L, we've got N, we've got D. We want to use this equation, but wait a second. L is not 10 times greater than X. We've got to find the angle. How would we do that? Yep. Yep. This would be L, right? This would be X. This would be theta. So you could find theta using the inverse tan function. Tan theta is equal to opposite over adjacent. Tan theta is equal to X over L. You'd solve for theta there. Okay, and you'd probably find that angle to be bigger than 10 degrees. Then you would go back and say lambda is equal to d sine theta over n. Now, we can do that every time, but we don't want to do that every time. Okay, having said that, guys, you can't use this equation unless you're measuring it from the central maximum, right? Make sense? Okay, so question like number 1, d sine theta over n would work perfectly fine if you found that angle. A question like number 2, the distance between antinodes that are right beside each other, the third and the fourth antinode. Now, unless you're talking about the central and the first antinode, well, then you can't really use that equation, right? Go ahead. That's a good question. It says distance between antinodes. What it really should say, what it means, and what it really should say is adjacent antinodes. What does that mean? Well, you're either talking about 2 and 3, or 16 and 17, or 2 of them right beside each other, meaning that n would be equal to 1. We find that sometimes, right? Our textbook is good, but we find that, sometimes they leave out a word that they mean something, and we kind of assume that. But yeah, on an exam, because an exam is such a small thing, it's only 50 questions, they can put a lot more time and effort into making up the question. A lot more people can proofread it than when you've got thousands of questions in a book, right? Okay, inevitably, little things sneak through a book that's that big versus a 50-question exam. Yep.
We're talking about situations where it's like useful.
Yep.
Are they going to be the exact answer, or are they going to be off?
That's a good question. Let's assume that you're dealing with an angle that's smaller than 10 degrees. Okay. The question, guys, if you didn't hear it, was, look, you gotta, what's x? What is the equation? XD over n times L. You got a problem. You've just calculated the value of x, and you found that L is bigger than 10 times x. So you're allowed to use this equation, even though it's not perfectly correct. It's a good approximation. You use that. Somebody else says, you know, I don't want to do that. I just don't trust it. I'm going to use this equation, d sine theta over n. And let's say this one, of course that's valid as long as you're measuring from the central max. Let's say this one, you get a value for the wavelength of 6.24 times 10 to the negative 7 meters. Should you expect to get the exact same answer here, 6.24 times 10 to the minus 7 meters? In most cases, yes. Now, if you don't, it is conceivable, because of rounding things, you could say 6.25 times 10 to the minus 7 or something like that. What happens there? Well, this one would be correct, of course. That one would be marked correct, absolutely, because that is the equation, really. With this one, we mark correct too. If you were under the 10 degrees, then yes, the test would be key to accept both answers. And I've seen that before. On a diploma exam, I've seen that when, you know, they give us questions that have been released from a previous exam. They give us the answer key. I've even seen questions where they've accepted 3 answers before. Not just 3 random answers. You know, not, you know, oh, if they made a mistake in rounding, we'll take this. No, they won't take that. Okay, but if you did it correct using a different method, but there's a rounding issue in there, then they'll mark that correct. Okay, good? All right, then. Well, let's take a look at this one. This one says a diffraction grating with 1,000 lines per centimeter. Light passes through the grating, an interference pattern is produced on the screen, blah, blah, blah. What's a diffraction grating? We have dealt with problems so far where we've had 2 openings, and we've measured the distance between those openings as d. That distance is really a distance per line, a centimeter per line. How many centimeters in between the lines? Does that make sense? Okay. 0.002 centimeters between the lines. Well, what you see in this question is not the amount of centimeters per line, but rather the amount of lines per centimeter. So what we're saying in this case is that we don't have 2 openings. We don't have 2 slits for the light to pass through. This time we've got hundreds or even thousands for every centimeter of distance. We've got 1,000 lines, 1,000 openings. Really, really close together. When the light passes through those 1,000 openings per centimeter, we get effectively, the small differences, but effectively the same pattern produced on the screen. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. The same equations work. Lambda is equal to xd over n times L, as long as the angle is under 10 degrees. And lambda is equal to d sine theta over n, as long as theta is measured from the central maximum. The only problem is we don't know what d is. We want the distance between the slits. We don't have that. We've got the number of slits per distance. So if you've got slits per distance or lines per distance, and you want distance per lines, what are you going to do? Flip it over. This is not d. This is 1 over d. If you want d, we're going to say 1 over 1,000, which is 1.00 times 10 to the minus 3. Now, what units would we have there for d? What units would it be? Centimeters, right? So if we've got 1,000 lines per centimeter, we've got 1.0 times 10 to the minus 3 centimeters per line. In other words, the distance between the lines is 1 over 1,000 centimeters. Now, we are going to want to convert that to meters. That's going to be 1.00 times 10 to the minus 5 meters. But please, please, please do this. Don't try to convert from lines per centimeter to lines per meter. Get it in centimeters first, then convert to meters. Why? Why am I suggesting that? I mean, it is possible to convert lines per centimeter to lines per meter, but why am I saying get it in centimeters first and then convert it to meters? How do you convert centimeters to meters? How do you do that? Go ahead, Chloe. Divide by 100, right? How do you convert lines per centimeter to lines per meter? You're going to multiply by 100. Is anybody confused by that? Converting lines per centimeter to lines per meter is multiply by 100? Why would we multiply when we're going from centimeters to meters? Well, centimeters is on the bottom, right? That's what it comes down to. Centimeters is on the bottom. And we're used to converting numbers that are on the top. If you're used to converting numbers that are on the top, then just keep going with that. In other words, get centimeters on the top and then convert it the way you're used to converting it. Okay, so it's possible to do it from here to lines per meter. I'm just saying, look, you're likely to get confused if you do that. Get centimeters and then convert it to meters, because that's not hard then. So we got D. D is 1.0 times 10 to the minus 5 meters. This is going to be L. This is going to be X, although we're in meters there. We're in centimeters. We want meters. The first order bright fringe, the central antinode, we're going to say N is going to be equal to, is an antinode a bright spot or a dark spot? Bright spot, so N is going to be equal to 1, 1 minus 0. We won't worry about that color again, right? Just worry about the wavelength. We want to use XD over N times L here, okay, because it seems like it fits best. Is it valid? What's the value of L? We got 4 meters. What's the value of 10 times X? 2 meters? Is L bigger than 10 times X? L is about 20 times X, right? So this equation is valid. X is 0.192. D is 1 times 10 to the negative 5. N is 1. L is 4. What do you get there? Kevin, what did you say you got there? 4.8 times 10 to the minus 7 meters. We should expect 10 to the minus 7, right? Visible light. I'll tell you what, when we're doing total internal refraction, your calculator tells you made a mistake, right? Error on your calculator. It doesn't happen here, but our little error on our calculator in our heads is this. If you don't get 10 to the minus 7, see the word error, because you've made a mistake probably if you don't get 10 to the minus 7. And there's a good chance it's been with a conversion or an N, all right? We're going to give you the 3 questions that go along with this. I'm going to caution you right now, at least one of these questions. There's at least one of these questions where you're going to want to use XD over N times L, where you can't. So check all 3 of them. See if L is more than 10 times X. If it is, great. If it isn't, then get theta and then use the other equation, assuming that you're measuring it from the central maximum. Okay? Okay, let's see what you can do.